All right. Thus far, as we wait for this to warm up here, the projector that is, thus far, really, I would say one of the main things that has been really hammered into us is that light has energy, or light is energy. But light can also exhibit particle behavior, meaning they can act as almost like a solid object. You know, in those packets of energy, those quanta, where they can hit electrons off metal surfaces, kind of like a pool table. Okay. Well, what this idea today is, it's going to start asking questions. Okay, and then it starts saying, well, there's also going to be some level of uncertainty when we start really diving really deep into the atom. Okay, and so that's where the wave nature of matter comes into play. Okay, we're not talking about the wave nature of light. We're talking about the wave nature of matter for this very brief moment. There was a doctoral candidate named Louis de Broglie who posited, I love when I use the word posited, basically who came up with the idea, or came up with the thought, that if light can have material properties, because again, they can act like solid objects like the quanta, then matter itself should exhibit wave properties. Are you matter? Are you matter? Y'all are matter, okay? So that means you should also be exhibiting wave behavior. You should have waves exuding off of you. And so, you know, you look at each other, you look at yourself, you're like, I don't see anything. Well, there's a reason for that. De Broglie demonstrated that the relationship between mass and wavelength are the reason for this wave behavior. So again, using this, again, very simple formula of wavelength is equal to, what's h again? Walk the, what do pirates do? They walk the plank, so Planck's constant, okay? Planck's constant, which again is a very small number, very small, divided by the mass times, now this time it's not frequency, it's actually velocity. Mass times velocity. Does anyone know what mass times velocity equates to? Momentum. So mass times velocity equals momentum. So think about this. Planck's constant is on top, it's the numerator. Very small, like I just mentioned, very small number. Divided by the momentum of an object, mass times velocity. So imagine what you know, that would look like. Well, it came to a point that basically the larger the object, this is an important point to note down. The larger the object, the smaller the wavelength. And really it all boils down to the momentum of the object. Okay? Really, when it comes down to it, the mass of the object. Okay? Now, if I were to compare myself, you know, we were to calculate using my mass and find that's wavelength compared to the wavelength of this little clicker, which do you think would have the smaller wavelength? I weigh more, just by a little bit. Okay. But it doesn't even matter. Do you see a wavelength coming off of this little clicker? No. Yeah, even with this little guy, it is still enormously large when compared to Planck's constant. But now let's kind of go the other way. Let's go to the atomic realm. Okay? where we are looking at electrons. Okay? Electrons have an incredibly small mass. So basically, what this is demonstrating is, on an atomic level, that is why we are able to have wave behavior noticeable and measurable from small particles like electrons and protons and everything like that. So yes, we do have wavelengths. Mathematically, we do. It's just so small it's imperceivable, immeasurable essentially. Okay? Now, we get to the interesting part. Besides, I mean, that's kind of neat to know that we all have wavelengths associated with us. But when we get into that idea and the measuring of, atomic particles, this leads us to what's called the uncertainty principle. And I'm actually going to read an excerpt from the textbook that if you don't have a textbook with you, it's okay. But if you do, when I tell you to open it up, because then you can follow along. It's no big deal if you don't have it. Okay, you just want to listen. Anyway, Heisenberg, he's a new scientist now. Heisenberg showed that the more precisely the momentum of a particle is known, so the more precisely the bottom part of this formula is known, the less precisely is its position in the atom known. And really, the main question is the electron. We're going to start talking about this. Okay? So, if we try to calculate the momentum of electron, we can do that. But then again, by doing so, we will not know exactly where it is. High level thinking right now. Okay? And so here's where that section of the textbook comes into play. So if you have your textbook, open up to page 230. I find this little excerpt fascinating. None of you have your textbook. Okay, you're going to have to listen like story time back in the day. Okay? So again, if you want to read this on your own, which I know you do this weekend, page 230, under these gold section called A Closer Look. It goes like this. Whenever any measurement is made, some uncertainty exists. Our experience with objects of ordinary dimensions like balls or trains or laboratory equipment indicates that the uncertainty of a measurement can be decreased by using more precise instruments. Remember the term sig figs? That's right along here, right along, that same notion. In fact, we might expect that the uncertainty in a measurement can be made indefinitely small. However, the uncertainty principle from Heisenberg states that there is an actual limit to the accuracy of our measurements. This limit is not a restriction on how well instruments can be made, but rather it is inherent in nature, meaning no matter how well we make equipment, by nature's laws, there will always be a certain level of uncertainty in our measurements. This limit has no practical consequences when dealing with ordinary sized objects like us, but its implications are enormous when dealing with subatomic particles such as electrons. To measure an object, we must disturb it, at least a little bit, with our measuring device. So think about any time you've ever measured anything with a ruler, what have you. You had to pretty much physically touch it. Well, when we start measuring electrons, we're not necessarily physically touching it with objects, but we have to use light. And as we know, light can act like a physical being. Therefore, it has to touch it. Imagine using a flashlight to locate a large rubber ball in a dark room. You see the ball when the light from the flashlight bounces off the ball and strikes your eyes. When a beam of photons strikes an object of this size, it does not alter its position or momentum to any practical extent. Imagine, however, that you wish to locate an electron by similarly bouncing light off it into some detector. Objects can be located to an accuracy no greater than the wavelength of the radiation or light that was used. Thus, if we want an accurate position measurement for an electron, we must use a short wavelength. And so what do we know about wavelength and frequency? Okay, short wavelength equals what kind of frequency? Big frequency, right? Inverse relationships. This means that the photons of high energy must be employed. The more energy the photons have, the more momentum they impart to the electron when they strike it, which changes the electron's motion in an unpredictable way. The attempt to measure accurately the electron's position introduces considerable uncertainty in its momentum. The act of measuring the electron's position at one moment makes our knowledge of its future position inaccurate. Suppose then we use photons of longer wavelength. Because these photons have lower energy, the momentum of the electron is not so appreciably changed during measurement, but its position will be correspondingly less accurately known. This is the essence of the uncertainty principle. There is an uncertainty in simultaneously knowing either the position or the momentum of the electron that cannot be reduced beyond a certain minimal level. The more accurately one is known, the less accurately the other is known. Although we can never know the exact position and momentum of the electron, we can talk about the probability. That word right there is what's going to carry us on through the remaining part of the chapter. Probability of it is probability of its being at certain locations in space. And so it goes on to the next line or two, basically saying we are introduced to a model of an atom that the probability of finding electrons of specific energies at certain positions in atoms. So I did not want to close that book, but I did anyway. So yeah. If you want to know one, you can't know the other with great certainty, no matter what. That's the extent of our accuracy in measurements. Okay, and got another little statement here saying, in many cases of us trying to figure out the momentum and the location simultaneously, the uncertainty of the whereabouts of an electron is actually greater than the size of the atom itself. So the uncertainty, the calculated uncertainty of where this atom could be, or where this electron could be, is larger than the atom we're investigating. So we have no 100% idea about that. All right, it's calculation time. Okay. I'm gonna get my stuff ready. It's calculation time. Calculation time. Okay. So basically, we're going to be using this equation. Okay. What is the wavelength of an electron moving with a speed of 5.97 times 10 to the 6th meters per second? The mass of an electron is 9.11 times 10 to the negative 31st kilograms. Okay, so just show you how they do this. Did it not have it? Of course it didn't have it. Okay, well, it looks like I'm gonna have to fix that slide as well. So here's how they solve this one. I don't have this one worked out in my book, so yeah, I do actually. All right, so all right. So just a few things, okay? The formula that we're going to be using, as I said, is wavelength is equal to Planck's constant divided by momentum, which is mass times velocity. We know what our mass is. Okay, mass of the electron is 9.11. times 10 to the negative 38th kilogram. We know what velocity it was traveling as at 5.97 times 10 to the 6th meters per second. Sorry, I got something in my eyeball. And we know Planck's constant is going to be 6.626 times 10 to the negative 34th joule seconds. Okay? So, one thing that we want to do is this, write everything out, and then go ahead and plug everything in. Again, Planck's constant, 6.626 times 10 to the negative 34th joules times second, divided by the mass, 9.11 times 10 to the negative 38th kilograms times the velocity, which is 5.97 times 10 to the 6 meters per second. Make sure I didn't do anything. Okay. So when we solve that, remember a joule has the unit, it's made up of units of kilograms times meters squared per second squared. Okay. This is represented by that joule. But we should know now that the unit for wavelength, in this case, is going to be meters. Okay? So the first step you want to do is calculate the denominator. Okay? Multiply these two numbers. Don't forget parentheses. Then divide Planck's constant by that product that you just calculated. Again, don't forget to use parentheses in there. And you should get an answer of 1.22 times 10 to the negative 10th meters. If you really want to get really creative, you can convert that into a metric unit by moving this over 1. And by moving it over to the left, it will reduce this number by 1 as well. So where you have 0.122 times 10. Oh, sorry. I didn't want to do that because I'm replacing this. My bad. Nanometers. Because nano is 10 to the negative 9th. So by moving this answer over 1, you could keep it in this answer if you want to, because technically it's correct. If you want to get fancy, it's good practice to try it. Move the decimal place over 1. It reduces the power of 10 by 1, and you replace it with nanometers. So let's look at our next question. Our next question is the following. Calculate the velocity of a neutron whose de Broglie wavelength is 500 picometers. The mass of a neutron is given in the table inside the back cover of the text. Since none of you have your textbook, I will give you that. Okay? So we got a wavelength of 500 picometers, neutron. You have to look at the mass. We have to calculate the velocity. Okay? So what do we know? Well, we're trying to calculate the velocity. We know Planck's constant is 6.626 times 10 to the negative 34th joule times seconds. The mass of a neutron is 1.67 times 10 to the negative 27th kilogram. And again, you want to make sure that your mass in this case is kilogram, okay? Because of this. Right here. What makes up joules. So in the back of your book, I think it's given to you in grams. You want to make sure, because in grams, it's 1.67 times 10 to the negative 24th grams. But you multiply by 1,000 essentially, divided by 1,000. And so by doing so, it becomes even more negative by three values. So, what was else? Oh, the wavelength. The wavelength was 500 picometers, but we can't have it remaining in metric values because we have to have it in meters. Okay, so we're going to take the 500 picometers, and so you want to also locate if you can find your metric prefix sheet that I gave you early in the year. That'll be helpful. So we're just going to do a little conversion here, where we have 1 meter over it's 10 to the 12th picometers, really small. And so when we do that, we're going to have somebody have their math because I haven't done this part yet in my head. Oh, yes, I have. Just kidding. We have 5.00 times 10 to the 10th meters. Sorry, 10 to the negative 10th. 10 to the negative 10th. 5.00 times 10 to the negative 10th meters for our wavelength. So, again, using our formula here, we got to solve for that guy. The first thing is I'm going to multiply both sides by mass. So I'm going to get wavelength times mass equals Planck's constant. That's not right. Don't listen to me. It's Friday morning. We're getting my brain working here. I'm going to multiply both sides by velocity. There we go. Promise you, I'll wake up here in a second. H times mass, or divided by mass. Next, I'm going to divide both sides by wavelength. And we get velocity is equal to H divided by mass times wavelength. And once I get that done, I'm going to place my numbers in there. Get Planck's constant, 6.626 times 10 to the negative 34th joule times seconds. Then divide that by mass, which is 1.67 times 10 to the negative 27th kilograms, multiplied by the wavelength, which is 5.00 times 10 to the negative 10th meters. What I want you to do, I want to see if you can get this calculated correctly in your calculating device. Now, a real quick question before you solve that is, what unit should we expect to have for velocity? Meters per second. Go ahead and give that a calculation. Need some more go juice. My brain's not working right. Okay, don't forget to use parentheses. Start with the denominator first. Anybody have an answer? Okay, let's see it. Let's practice. We're going to come back to that. Anybody else have a different number? Yeah. 794 or so. That's correct. What I want you to try, use parentheses when you multiply the bottom. Try again. Don't forget it's negative 27. That's negative 10. This is, are you putting the negative signs in there for the powers? Okay. Try again. We got time. Did it come out that time? Good. Good. Excellent. So, a few things to remember when using this formula. Okay. The V, the velocity, is going to be in meters per second. And the mass of whatever particle you're using must be in kilograms for your calculation. Okay. Questions on this? Okie dokie. That's all I got for today. Again, I plan on going over the quiz Tuesday, just to touch base with it, just so when we move forward, we'll be in good standing. All right, I'm going to stop this recording.